Hey folks, how y'all doing? We're starting chapter 13 today. This is um, the section on vector functions and curves in space. Before we get started, actually, I want to make a couple of announcements. Face-to-face classes should start back up on Monday if everything goes well. And one of the some of the feedback that I've gotten from you this week over the extra credit assignment has been that, well, just like the national election, y'all are very evenly split over whether you prefer to meet face to face or whether you prefer to meet over Zoom. And I understand that circumstances have changed over the course of the semester for some of you, and some of you are now at home when you had started out on campus, or less concerned or more concerned about the epidemic than you had been at the start of the semester. But there was a request to continue the Zoom classes, even that we've been doing. So what am I going to be doing at least until Thanksgiving, and then after Thanksgiving, everything is on Zoom because we don't meet face-to-face after Thanksgiving. But for the next week and the week after that, we'll meet in a classroom at the regular times, Monday, Wednesday, Friday. If you want to come by, I'm happy to meet with you face-to-face. And then I'm going to schedule a couple of Zoom classes in the evenings on Monday and Wednesday. I'm going to shoot for 7 to 7:50. And for people who would prefer to have Zoom classes. And again, this is just until Thanksgiving. And then after break, they'll go back to the usual class times. Okay, I hope to see some folks there. All right. If you have not already completed the extra credit assignment, and there are a few of you who haven't, but not many, but if you haven't completed it, it's due today. So go ahead and get it taken care of. It's only a couple of questions. It doesn't take you very long. And then the next graded assignment is the WebAssign review, which is due on Thursday. And so you've got a whole week to work on that. But go ahead and get started on it so that you can ask questions and you're not waiting until Thursday night to ask them, okay? So let's go ahead and get started. What is a vector function? A vector function takes a number, a single number, often time as an input. So what we've been looking at so far in this course are functions where the output takes multiple inputs, like z equals f of x, y. We have a partial derivative with respect to x and a partial derivative with respect to y. Many inputs and one output. The multivariable part was in the input. What we're looking at here is a vector function where we have an x-coordinate and a y-coordinate and maybe a z-coordinate. And only one input, but then it generates multiple coordinates. So one input and multiple outputs. The different coordinates of a vector. Okay? For example, when we write this function, r of t equals 6t comma t squared comma sine t, I'm computing three different things based on the value of t. This is an example of what we call a vector function. Okay, so this is multivariable in the input, or I'm sorry, in the output, whereas what we've been doing is multivariable in the input. So when we talk about the domain of a vector function, we mean the set of values that make the entire vector defined. So as an example, this is, I'm hoping not too complicated, if my vector function is t comma 1 over t, then 0 is not in the domain, even though I can plug in 0 over here and get t equals 0, I can't plug in 0 into the y-coordinate. I have to get the entire vector in order for a point to be in the domain. So 0 is not in the domain because it's not in the domain of one of the parts. Okay? So let's try an example of that. Let's find the domain for this vector function. So my x-coordinate is the natural log of t plus 1. My y-coordinate is t over the square root of 9 minus t squared. And my z-coordinate is 2 raised to the t power. So the x-coordinate is undefined because we can't take the natural log of 0 or a negative number. So it's undefined when t is, when t plus 1 is less than or equal to 0. And so if I make a number line for t, then 0 and everything to the left of 0, this is bad. If I plug in any negative number, I'm sorry. Let me back that up. I have to, one more thing, I have to bring the 1 to the other side. T has to be less than or equal to negative 1. So at negative 1 and to the left, everything is bad. And to the right, everything's good. But we're not allowed to have any values of t that are to the left of negative 1, because then this will still be negative and we can't take the natural log of that. Okay? So what about this function? This is undefined. When 9 minus t squared can't be 0, because then we're dividing by 0, and it can't be less than 0 because we can't take the square root of a negative number. So when 9 minus t squared is less than or equal to 0, if I add t squared to both sides, that's 9 is less than or equal to t squared. So this is tricky because this is saying that t is greater than 3 or t is less than or equal to negative 3. So less than or equal to negative 3 is already covered. So this side is already covered. Because anything that's less than negative 3 is less than negative 1. But this side isn't. And so starting at 1, 2, 3 and going on to the right, that's also bad. For example, if t is equal to 5, 9 minus 5 squared is a negative number, and we can't take the square root of a negative number. What about the last one? What about 2 to the t? This is always defined. If the base is a positive number, then t can be any value. If the base is greater than 0, the exponent can be any real number. So we don't get any new places that are bad from the z-coordinate. And so the domain is everything from 1 up to 3, but not including 1 and not including 3. And so the solution is -1 less than t less than 3. Or we can write that as the interval from -1, and I'm using parentheses and not square brackets to indicate that I'm not including the endpoints. The interval between 1 and 3 using parentheses notations. Either of these is correct. All right? So let's keep going. If we want to graph a vector function, the graph is a curve in space and not a surface in space. That is, the graph is going to, instead of looking like a plane or a cone, it's just going to look like some kind of curve. It's not going to have any thickness to it. It's just going to travel through space and move around. So let's try to sketch this curve here. If you want, it might help to just make a couple of values to get you started and see what's happening. So we're going to make a table. When t is equal to 0, this is an easy place to start. The x-coordinate is 0. Sine of 0 pi is 0. Y is equal to 0. And z is a cosine of 0, which is 1. All right. When t is, I'm going to do 1/2. So we're going to, when I multiply by pi, I get pi over 2. Sine of pi over 2 is 1. And then y is 1/2. And cosine of pi over 2 is 0. Then we go to t equals 1. Sine of pi is 0 again. Y is just t, so that's 1. And the cosine of pi is -1. And then 1.5. I'll say 1.5 here. Sine of 3 pi over 2 is -1. Y is now going to be 1.5. And z is going to be 0 again. And then when we get to 2, we're looking at 2 pi, and 2 pi is going back to the original point on the circle, but the y-coordinate is not moving around the circle, the y-coordinate is moving forwards to 2. And so what does this look like? We start at x equals 0, y equals 0, and z equals 1. There's a -1 back here and a -1 down here. And then when we move out to the next point, y has moved out to 1/2. And the x-coordinate has moved up to 1, but the z-coordinate has come down to 0. Then by the time we get to y equals 1, this point here, the z-coordinate is down to -1, but the x-coordinate has come back into 0. Then we get to 1.5. The z-coordinate has come back up to 0, but the x-coordinate is back here at -1. And then we finally get to y equals 2, and the z-coordinate has come back up to +1, but the x-coordinate is over here at 0. So it's come back up to here. And what's happening is we've got a shape that spirals around the y-axis, that in the x and the z coordinates is moving around in a circle, but in the y coordinate it's moving forward in the y coordinate as the x coordinates and the y coordinates are going around. And so we have a shape that looks kind of like a spring. Okay? That's what's going on. That X and Z form a circle. But it's a circle that as we go around and around and around the circle, the y-coordinate is moving outwards, and so we're circling and projecting outwards like so. So that's what's happening. It's looping around the y-axis and moving forwards as it goes along. And if we did negative values of t, it would also do the same thing or in the negative direction. Like so. Okay? So that's what this curve looks like. There's no surface to it. There's no area. There's no volume because it's just a thin strand going through the space. But that's what the graph looks like. Sometimes if the graph is difficult to draw or to visualize, we use the projections of the graph to help understand the curve better. And here's kind of what I mean. If I go back to this previous graph, if I looked at what's happening on the XZ plane, and I'll use red for the XZ plane here, it just looks like a circle. It's just zooming around in a circle form. But if I look at what's happening on the YZ plane, I'll use blue for the YZ plane, it's moving forward in the right direction, but it's oscillating in the Z direction. And so this is a picture of what's happening in the XZ plane. This is what's happening in the YZ plane. So sometimes it's easier to draw the projections than it is to draw the actual graph. So let's try drawing the projection of this curve onto the YZ plane. So when they say the YZ plane, we don't care about the X coordinates. We're only caring about the Y and the Z coordinates. So for this problem, we only care about Y and Z. Okay, so we're looking at what's happening in the Y and Z direction. All right. I'm going to leave off t equals 0 because 0 to the negative 3 power is undefined. But let's look at what happens when t is equal to 1. Then y is equal to 1 and z is equal to 1. When t is equal to 2, y is equal to 8, but z is equal to 1 over 8. When t is 3, y is equal to 27, but z is equal to 1 over 27. And so on and so forth. The y-coordinate is getting bigger because it's t cubed, but the z-coordinate is getting closer to 0 because t is negative, t to the negative 3. And so if we plotted these points, this is what's happening on the y-axis and the z-axis. The first point is 1, 1. The next coordinate is 8, 6, 7, 8, 1, 8, which is pretty close to 0. And then the next coordinate's got to be way out here at 27, and it's got to be so close to 0, we're not going to be really able to tell this. The y-coordinate is getting big very fast, and the z-coordinate's heading down to 0. And if we went in the other direction, we'd find that we had a vertical asymptote because at t equals 0, the z-coordinate is undefined at this point. And so we have this sharp inflection right here at 1, 1, where it's going up to this axis and has an asymptote up here and an asymptote over here. Okay? This doesn't show us any information about the x-coordinate. This is just what the curve looks like when it's been projected onto the y and z axes. Okay? And if I could see the front view and the side view and the top view, for example, if I could see multiple views of this shape, I might be able to get a sense of what that shape is, even if I couldn't draw the entire thing in 3 dimensions. Okay? Let's move on to the next example. Let's try to calculate some vector equations here. We want to come up with a vector equation for the line segment that joins the point -2, 1, 0. So that's this point here, to the point 5, 2, -3. So 5 on the x-axis, 2 on the y-axis, and then 3 units down from there. So that's way down here at the bottom. And we want to create a line segment that connects this point down to this point. All right, well, that's close. There we go. All right. There's more than one way of doing this, but this has got to be sort of the idea. We want to create create a vector function that has an x-coordinate and a y-coordinate and a z-coordinate. And since this is a line, well, we know what the equation for a line looks like. The x-coordinate is going to be mx plus b, or mt plus b, because my variable is t. Let's say m1t plus b1. And the y-coordinate is going to be m2t plus b2. And the z-coordinate is going to be m3t plus b3. This is what lines look like. Y equals mx plus b. This is the idea we're using, except that my x is an output now, not an input, and t is the input. So mt plus b, mt plus b, and mt plus b. So we pick a time at which the trajectory will start at P and a time in which the trajectory ends at Q. So we're going to pick times where the trajectory goes through P and Q. And you can do this for any values, but if we use 0, the calculations are so much easier. So I'm going to let t equals 0 be the starting time and t equals 1 be the ending time. So we're going to get to this point at t equals 0, and we're going to get to this point at t equals 1. And now this tells me that r of 0, which will be m1 times 0 plus b1, and m2 times 0 plus b2, and then m3 times 0 plus b3, has to equal -2, 1, 0. Well, that's really easy to solve. That's why I suggested using t equals 0 for a starting time. I don't have to worry about the m's. This tells me that, there it is. Sorry about that. Lost my pen for a second. B1 is equal to 2. Or sorry, B1 is equal to -2. B2 is equal to 1. And B3 is equal to 0. So now let's look at what happens at the time 1. R of 1 is equal to m1 times 1 minus 2, now that we know what b1 is, m2 times 1 plus 1, and m3 times 1 plus 0. And that equals 5, 2, and negative 3. Well, that gives you enough information to solve for m1 and m2 and m3. m1 minus 2 is equal to 5, so m1 has to equal 7. m2 plus 1 is equal to 2, so m2 has to equal 1. And m3 has to equal to negative 3. Okay? And so my final answer is my vector function will be 7t minus 2, comma, 1 times t plus 1, so t plus 1, comma, negative 3t. And we can double check that and make sure that when we plug in 0, we get p, and when we plug in 1, we get q. All right. So that's how we find the vector equation for a line segment. This line segment is only valid between t equals 0 and t equals 1. And we should sort of specify that if we want to reference the line segment and not the entire line. Okay? All right. Let's do a harder one. Find a vector equation for the intersection of the cone and the plane. So here's what's going on. We've got our coordinate system here. We have a cone here. And we're going to take a plane in that with no x coordinate. It's going to be the plane z equals 1 minus y. And slice through that. When we slice through this, we're going to get a slanted ellipse through the cone. That's the shape that we're getting. This is the intersection. And we'd like to come up with a vector equation for that intersection. Okay? So because this is the intersection, we're going to set these two equations equal to each other. So on the left side, I'm going to get 1 plus y equals to square root of x squared plus y squared. What I'm going to do now is to try to solve this. So I'm going to square both sides. Let's see, this gives me 1 plus 2y plus y squared is equal to x squared plus y squared. The y squareds cancel. And so I'm left with 2y is equal to x squared minus 1. And so y is equal to x squared minus 1 over 2. Okay? And so now I have y in terms of just a single variable. And so what we're going to do now is we're going to take the variable here and assign that variable equal to t. So we're going to assign x to equal to t. Then y is going to equal to t squared minus 1 over 2. And z is going to, I'm using this because it's less complicated than this one. Z is going to equal to 1 plus t squared minus 1 over 2, which is actually the same thing as if I write this as 2 over 2 plus t squared minus 1 over 2. 2 and negative 1 is positive 1, so we get t squared plus 1 over 2. And that's, in a sort of nice form that matches up with the form for y. I could have used this at this step. I would have just gotten a harder expression to simplify. We could use either equation for z, but pick the one that's easier. And we end up getting this for the equation. R of t is equal to x is just t, y is t squared minus 1 over 2, and z is t squared plus 1 over 2. And this gives me the equation for this ellipse that's at an angle relative to the xy plane. All right. So let's move on. If we want to talk about intersection and collision points, if we have two different trajectories, two different vector functions, an intersection point is a point in which both of the trajectories pass through the same point. The two trajectories intersect at this point, but they may pass through this point at different times. If the first trajectory passes through at time t equals 0, and the second trajectory passes through at time t equals 3, then they don't run into each other, they just happen to cross over the same point. We define a collision point to be trajectories to be a point that both trajectories reach at the same time. They have to get there at the same time in order to collide. All collision points are intersection points, but it's not true the other way around. We have intersection points that are not collision points because the trajectories reach that point at different times. Okay? We're going to do some examples of finding intersection and collision points. Collision points are easier, so we're going to do these first. I want to find the collision points for these two trajectories, these two vector functions. All right. So if they collide, then the x-coordinates will be the same. And so will the y-coordinates. So when the x-coordinates are the same, we get 2t squared minus 5t plus 14 equals to t squared plus 2t plus 4. The y-coordinates would be the same, would be negative 3t squared. That should be t cubed. I'm sorry about that, because this is a t squared term. Plus t squared plus 2t minus 16 is equal to 5t cubed minus t squared plus 2t minus 88. Okay? Because this equation has cubed terms and this equation has squared terms, this equation looks easier, so let's work with this one for a while. I'm going to bring everything over to the left side. So when I subtract t squared, I get t squared. Then I subtract 2t, I get negative 7t. And I subtract 4, and I get 10. And then that factors into t minus 2 and t minus 5. And so we get two solutions. T equals 2 and t equals 5. And those are the times when the x-coordinates match. So now, our thought bubble here says the x-coordinates match at this time, at these times. What about the y-coordinates? Well, we can just test them over here. Let's see what happens. At t equals 2, the left side is going to be negative 3 times 8 plus 4 plus 4 again minus 16. And that's equal to negative 40 plus 8 is negative 32. Where am I going to go again? There you go. Negative 32. And the right side is equal to 5 times 8 minus 4 plus 4 minus 88. That's 40 minus 88 is negative 48. So that didn't work so well. So let's try what happens now at t equals 5. We get negative 3 times 125 plus 25 plus 10 minus 16. That's negative 375, negative 340, negative 356. And over here, we're going to have 5 times 125 minus 25 plus 10 minus 88. Well, I can already tell this is going to be a large positive number. This is 625 minus 25 is 600, 610 minus 88 is 522. And so it turns out that there are no collision points for these two functions. At time t equals 2, the x-coordinates don't match, and at t equals 5, the y-coordinates don't match either. Okay? All right. Okay. So let's move on. I'll go ahead and write out the answer here. The solution is no collisions. It's harder to find intersection points because we have to allow for the possibility that the two trajectories arrive at different times. And since the times could be different, we have to use different variables to represent them. So this example's worked out in the slides, but I'll walk through this process with you. We want to find the intersection points for these two functions here. T minus 3, t squared minus t minus 4, and t plus 2, 6t plus 34. Because we can allow for the trajectories to intersect at different times, I can't use t in both trajectories. So I'm going to use t in this trajectory, and I'm going to use s in this trajectory, and there should be a t here that's missing. It's missing up here too because I cut and pasted. There we go. And now we're going to set these equations equal to each other. But the problem now is that this is a system with two variables and not just a bunch of equations that we could solve for t. And so we're going to have to work on this as a system now. So on the next slide, we're going to take the top equation and solve for s in terms of t. We get that s is equal to t minus 5, and we're going to substitute that into the other equation. T squared minus t minus 4 is going to be 6 times t minus 5 plus 34. 6t is 6t. 6t minus 5. 6 times negative 5 is negative 30 plus 34 is 4. Bring everything to the other side, and we get 2 times negative 1 and positive 8. Okay? Well, then, when I go back and check these, since these are t's, we check them in the first trajectory because it was the second trajectory that replaced s's in. So when we check t equals negative 1, negative 1 minus 3 is negative 4. Negative 1 squared is positive 1. 1 minus negative 1 is 2. 2 minus 4 is negative 2. And then when t is equal to 8, we get 5 and 52. So that's where this trajectory is at t equals negative 1 and t equals 8. We verify this now by checking this trajectory, but using the s times instead of the t times. Since we found that s was t minus 5, then when t is equal to 1, s is negative 6. So over here, I'm going to plug in negative 6 and see what happens. At negative 6, this is negative 4, and this is 36. No, negative 36 plus 34 is negative 2. And so we also get negative 4, negative 2. And when s is equal to 3, that's 8 minus 5. We get 5 and 52. And so both of these are intersection points. There are 2 intersections. One's at negative 4 and one's at negative 2. And one's at 5 and 52. 52. We hit this first intersection when t is equal to negative 1 and when s is equal to negative 6. So if my time is in seconds, they reach this intersection point 5 seconds apart from each other. And then they reach this intersection point 5 seconds apart from each other. Because one reaches at t equals 8, but the other one reaches at t equals 3, or time s equals 3. Okay? So that's how this works. We have to find an intersection instead of a collision. We have to use a different set of times for the second trajectory. So now let's try one without the notes haven't already worked out. These two particles travel along pair of curves. Do they collide and do they intersect? So let's answer the collision question first. If they collide, then t equals 1 plus 2t, and t squared is 1 plus 6t, and t cubed is 1 plus 14t. Collide has to occur at the same time, and so I don't have to change variables. This is the easiest equation to work with. We get, when I subtract t, 0 is equal to 1 plus t equals negative 1. So over here, that's negative 1. Then t squared is equal to 1, and 1 plus 2 times negative 1 is negative 1. Those are not equal. T cubed is negative 1, but 1 plus 14, oh, good Lord, that's negative 13. Those are not equal. And so the time that makes the x-coordinates match doesn't make the y-coordinates and z-coordinates match. And so they do not collide. There is no time that makes all 3 coordinates equal. Okay? So then do they intersect? So then we'll do this again, but this time we're going to change the right side from a T to another letter. We'll call it S. t squared equals to 1 plus 6s, and t cubed is equal to 1 plus 14s. Okay? By the way, over here, I think I copied this down wrong. This should have been a 6 and not a 2. And so this would have been a negative 5 instead of a... They're still not equal, but I caught that when I was writing this over here. All right. If t is equal to 1 minus 2s, then I'm going to make a substitution into this equation. I'm going to get 1 plus 2s squared is equal to 1 plus 6s. Let's work on this equation for a moment. This is going to be 1 plus 4s plus 4s squared equals to 1 plus 6s. When we do this, the 1's cancel. And we end up with negative 2s plus 4s squared is equal to 0. I'm bringing a 6s to the other side. And I can factor out a 2s. 2s times negative 1 plus 2s is equal to 0. And so this is s equals 0. And this says negative 1 plus 2s is equal to 0. So 2s is equal to 1, and so s is equal to 1/2. So we have the possibility of having an intersection, but we haven't checked the t cubed equation yet. So do they intersect? When s is equal to 0, t is 1 plus 2s, which is 1. And given that, the x-coordinates are 1 equals 1 plus 2 times 0. The y-coordinates are 1 equals 1 plus 6 times 0. And the z-coordinates are 1 cubed, which is still 1, equals 1 plus 14 times 0. And so we get 1 for the x-coordinates, 1 for the y-coordinates, 1 for the z-coordinates. So they do intersect at this point. Let's see what happens when s is equal to 1/2. Then t is equal to 1 plus 2 times 1/2, and that is equal to 2. So the x-coordinates will be t is equal to 2, and y is equal to 1 plus 2 times 1/2, which is 2. The y-coordinates is going to be t squared is 4, and t squared is 4, and 1 plus 6 times 1/2 is 1 plus 3, which is also 4. And then for the z-coordinates, t cubed is equal to 8, and 1 plus 14s is 1 plus 7, which is also 8. And so all of these check, and so 2, 4, 8 is also an intersection point. And so they do not collide. But they do intersect twice at 1, 1, 1 and at 2, 4, 8. Okay? What we'll look at on Monday is problems involving taking derivatives and antiderivatives of these curves, and have a fantastic weekend. Y'all take care.